I'm going to talk a little bit about some of the open challenges for the next generation of programming agents, of programming automation, right? This idea of how we automate programming has been around all the way back to the very beginning of computer science, right? In fact, Alan Turing, in a famous lecture in 1945, talked about how, basically working with computers is never going to be boring, because as soon as some part of it becomes boring, then we just automate it, and then we can jump on to the next not boring thing, right? And we've basically been doing this over and over again ever since, right? For example, when the first compilers came around, right? Fortran was touted as the Fortran automatic coding system, right? The goal is that you have the machine program itself, just as good as the human, but with no bugs, right? And today it sounds a little bit laughable given the technology that we have, and yet you could argue that they succeeded, right? What people called programming back then, working in assembly, figuring out where to put all your registers, nobody does that anymore, right? And the kind of bugs that people made as part of that process, you don't have to worry about those bugs anymore, right? We've learned how to make new bugs and new kinds of mistakes. But I think we can all argue that we're really in a different era today, right? AI programming really is here. We have all of these tools that are capable to write code at a level of proficiency that even a year ago was kind of difficult to imagine, right? And it's transforming the way we write code and the way we think about the process of building software. And I think we're only at the beginning of these revolution, but it does lead to the question of what's left for people like me who like to do research in this space to do, right? I started working on this problem of programming automation a little over 20 years ago now. And for most of those 20 years, people would ask me, why are you working on this problem? It's so hard. Machines will never be able to program for us. Programming is this thing that just requires all of our human capabilities. And then suddenly, from one day to the other, people started asking me, why are you working on this problem? It's solved. There's already all these tools. They already do this for us. What else is there to do? And so I want to argue that we're not done yet. There's still some way to go. And in particular, there's a few problems that I think are very critical that we need to address in order to really get to the full promise of AI programming. The first bottleneck that we have right now is analysis, right? These systems are really good at producing lots of code, not as good at helping us understand all of these code. There's also still bottlenecks around the really high complexity software, right? Your very intricate concurrent data structures, for example, right? Your really important compute kernels. And I argue that there's still a long way to go when it comes to the right interaction model, right? The machine can only build us the software we want if we're able to clearly tell it the software we want. And so I want to talk especially today about these two because we don't have that much time today. And so I want to start talking about this analysis bottleneck. So if you go back to the early 2000s, right, Crocs were a cool new thing that people were wearing. Facebook was actually fun to use, and you could use it to interact with your friends instead of random influencers. But if you were in the programming systems community, you probably also remember the early 2000s as the golden age of program analysis, right? For many, many years, people had been thinking about how to reason mechanically about code. Compilers, for example, did some analysis to figure out some optimizations. But it was really in the early 2000s that there was a big push to, can we build tools that can reason about our code, that can tell us where the bugs are, that can prove our existing software free of bugs. And there was enormous excitement about this. There were a lot of major success stories. And in fact, today, a lot of, I wouldn't say a lot, but the largest companies, places like Microsoft, Google, Amazon, they do have teams of people building these kinds of tools and applying them to their code bases to help them find bugs and ensure software quality. But it never quite got there, right? Most developers have probably never used a static analysis tool in the way that back in the early 2000s was intended. But it was back then that I actually started working on this problem of how do we bring automation to programming. And the fact that, at least in principle, it was possible to analyze a piece of code and find the bugs was really inspirational to, could we go further and could we actually have the machine not just check for bugs, but actually help us write the code. But very quickly we realized that, well, actually, maybe we don't need to verify the code, right? Maybe we can settle for just writing code as well as the humans, right? Writing code that is going to pass the unit tests, writing code that is going to satisfy some examples, input-output examples that we give it. And that turned out to work pretty well, especially once we had deep learning, for example, to help us make this more effective, and then foundation models came around. And you could argue that this is exactly what the community as a whole did. Right now we have systems that can write code as well as humans, maybe even a little bit better. But it turns out that this now creates a bottleneck, because if you just take a regular software development organization where maybe you have some developers, there's a manager overseeing them, right? And these developers produce code that the manager helps code review, that the manager helps set direction and is in charge of the overall structure of this piece of code. It works. That's how a lot of our software has been built for many years. But now, suddenly, all of these people have Claude code, and now there's a lot more code out there, right? It's much harder to keep up. And here's the thing, right? These tools are as good as the human developers, maybe a little bit better, certainly way faster, but they're still making mistakes. And if you don't catch them, you're going to end up with this major vulnerability as part of your software. Now, you might say, well, didn't you hear the news, right? We have Mythos now, and it's able to find all the bugs, and it's able to find all the vulnerabilities. I would argue that, and acknowledging, first of all, that I haven't actually tried it. I'm not in the golden list. But any tool that is able to find a lot of bugs, but not all the bugs, will find, however many bugs we'll find, and sort of by definition, the bugs that will remain are the bugs that this tool cannot find. And now you're just waiting. Maybe the next generation tool will find it, and hopefully I'll get my hands on it before my adversaries, my attackers, do, right? And if I don't, then that will be a problem. But it doesn't have to be that way, right? Maybe sound program analysis can help, right? If you go back again to a lot of these ideas from the early 2000s, it is possible to build analysis that will go and analyze a piece of code and find all the bugs, right? So you give it, it finds all the real bugs. Why doesn't anybody use this? Well, because it will also find lots of non-bugs and tell you that they're bugs and consume lots of developer hours going and pouring through these bugs just to find that, oh, no, actually, it's just the analysis being silly. And if we had just written the code a little bit differently, the analysis would realize that this is not a real bug and that this is not actually a problem, right? And for a tool that is to be used by human developers, this is not a very good value proposition, right? If you have to go through 100 ports of fake bugs just to go and find the one that is actually for a real bug. This is not a tool that anybody's going to want to use. This is not a tool that is going to be very successful. And if on top of that, this tool requires days and days of work by PhD-level experts in order to configure so that it actually works on your code base and so that it's tailored for the kind of idioms that are used in your code base and for all the libraries that are used in your code base, then suddenly you have a tool that is just not going to work very well. But today, we have the ability to get past that, to get past a lot of those limitations, and especially when you are in a world where the actual coding aspect of software development starts dropping in price and cost dramatically, where that part of the software development is now more or less free, and where the bottleneck is now your ability to analyze that code and to think about that code. A lot of the certainties that we had from before that told us why these kind of tools would not work, suddenly they're different, right? And suddenly we can start actually taking advantage of some of these tools. So I want to talk a little bit about some of the research that my group is doing in this space, and to give you a sense of some of the possibilities that we have by combining all the advantages that we get from language models and from AI tools in general with a lot of the technology that we have from before for how to reason rigorously about programs. And so some of the work that I'm going to be talking right now is led by my student, Michael Wang. And so I'm going to get a little bit technical here, but hopefully it'll be fine. So I want to tell you a little bit about how do we actually reason about a piece of code mechanically, right? How does a program analysis look at a simple piece of code like this and actually figure out what this piece of code is going to do and whether something might go wrong as this code executes, right? So the way an analysis might go about this is that it will start interpreting this piece of code, right? And it will build a model of the data structures that this code is building as it executes, right? And so, for example, you might have an object that is pointed to by X, and it has some link to some node with some information. Maybe it has a head and a tail for this list. And as you iterate, the state of the code, the state that this code is processing is changing, and you're creating new nodes, allocating new nodes, right? And this is also what happens when you just execute this piece of code. But if you want to analyze statically, what you want is you want to abstract what happens in any one concrete execution into a summary that tells you what's going to happen in all possible executions, right? Regardless of the input, regardless of the environment. And in order to do that, oftentimes what you have to do is lose some information. For example, maybe you decide that all of these nodes in the list, we can abstract them to a single summary node that summarizes the whole content of the list, that tells you about all the things that might happen, right? This is basically what a static analysis tool is doing internally. And when it does this, it's now able to build the summaries about everything that's going to happen in the state that this code is manipulating. But this process of abstracting and compacting objects turns out to be very delicate, right? If you do it right, it allows you to reason about even a potentially very complex algorithm very efficiently. But if you do it wrong, you might lose critical information about how this code works. And this is what ends up leading to all of these false bug reports, right? Things where it looks like something could go wrong, but only because of the information that was lost at this part of the process, right? For many years, people who designed this analysis have spent lots and lots of time trying to figure out, are there some heuristics? Is there some clever way to decide what information is OK to lose, what information is not OK to lose? And the wish of everybody who works in this field in the back of our head has always been, if only you could have a really, really clever expert monitoring this process and telling you, nope, that's not the right thing to do there. Yes, that's the right thing to do at this point. Nope, if you lose that information, it's going to be terrible, and you're not going to be able to have the precision that you want. Obviously, no actual person would want to do this. It's just too much, too complicated. But today, we have language models that can actually help us do this. And they can bring to the table capabilities that none of the prior heuristics had, right? You can actually go and understand what this piece of code is trying to do. You can understand the language model actually has a lot of background knowledge about what your class names mean, about what your function names mean, about what your variable names mean, about what the overall goal of this code is. It can go and read its documentation. And at the same time, it doesn't get bored. It doesn't get annoyed. It does expect you to pay lots of money to Anthropic, but that's a different story. And so you can do things like this, right? For example, if you have some piece of code, maybe there's some object representing students, there's some object representing teachers, you might be able to abstract and merge together all the objects representing the teachers and all the objects representing the student without too much loss of precision. But if you were ever to try to merge all of those into a single node, suddenly you have these dramatic loss of precision. This is what the language model can actually help you avoid. And we've started some small-scale experiments around in this direction. And we can already see that when analyzing individual functions and analyzing small modules within the code, you can already achieve much better precisions than prior static analysis. But it turns out that if you actually want to apply this to real code, this is only one part of the bottleneck. You have a much bigger bottleneck, which is that any real application is not made up only of code you can see. Yes, you have the code you can see, and you can analyze it. You can go through the process that I just described. But then you have APIs. You have libraries. You have built-ins that are part of the language. And they're constantly changing. They're constantly evolving. And the program analysis has no idea how to access this. It has no idea. It doesn't get to see the source code. Some of them might be just proprietary. And so this turns out to be a major bottleneck if you're trying to actually run this kind of analysis on real code bases, right? And so it turns out we can automate this too. So we've actually built a whole system that actually allows you to start with a code base, and it's able to identify the libraries that you're using. It's actually able to then, from there, build a schema for the API, automatically generate test cases that exercise that API so that the agent can actually understand how this works, right? And see what happens when it sees different inputs, when it sees different outputs. It's able to then generate a model of how this library works. Not just some other implementation, but truly a model that captures the essential aspects of this library, the aspects that are important, that a user can actually inspect or ask questions about its behavior and whether it captures particularly important behaviors that you care about, and that is validated against the test data, against the true execution data, so that you can then directly go and do analysis on your existing code, right? And completely automatically, for example, we're able to go and analyze JavaScript code, right? And JavaScript is notorious for the fact that analyzing JavaScript requires models of all of these other infrastructure that any JavaScript program directly interacts with, right? You can't understand the JavaScript program if you don't have some kind of a model of the DOM, for example, and know how it's going to react to various interactions, right? And we're able to even go to real packages out of the Node Package Manager, for example, find the most popular packages under 10,000 lines of code. And if you compare with existing tools, right, even tools that have been built over a long time, that still cannot run in these packages because they don't have the requisite models, and we're able to generate those models basically on demand, right? And one of the exciting things about this combination of the language models with traditional program analysis is that it opens a whole new dimension for collaborating and interacting with these with the tools, right? And this leads me to the next thing that I want to talk about in the few minutes that I have left, which is interaction, right? Now we have these tools that can build anything that you tell them to build, as long as you're able to describe it in enough precision and with enough detail and be able to instruct it in the right way, which people might argue, well, yeah, that's called programming, right? Describing what you want with lots of precision and lots of detail, that is programming. But if we think about when we're interacting with actually other humans to help develop code, one of the things that makes it very effective is that we have all of these different channels of communication, right? Not only can you pair program, not only can you go to a whiteboard and explain your ideas, you can build up this common language and this common understanding over years of working together, right? And this is what makes it very hard, especially when you have an already existing mature code base, right? Where when you're talking to another person who's worked with that code base for a long time, you've developed a language, you've developed a way of talking about the code, you've developed a shared understanding, and we have so many different channels to interact and communicate that it's very difficult for the tools that exist today to replicate that. And so we've actually been thinking about some of these issues for many, many years. And I want to give you an example, for example, of something we did all the way back in 2017, right? Back when we were still at the stage of nothing works and nobody believes it's ever going to work. So we were thinking about this problem of how do we get the machine to help us with the code, right? And we were thinking in particular about this problem of reuse. You have a piece of code, you have a framework that already does something that you want, right? Maybe you have this framework for writing editors, and it already has all the functionality that you need to build a structured editor for your language. And you want to reuse it, and it's great as long as you can find out how it works, right? And even nowadays with the very powerful language models that we have, this works great if you're dealing with a framework that is publicly available and lots of people use and the model knows a lot about it. It's not so great if you have an internal framework that only the people in your company have access to and know how to use, right? And sometimes even figuring out what is the right language to describe what you want the system to do is messy, right? For example, we were playing back then with this Eclipse framework where you had even something as simple as syntax highlighting required not just a scanner, but a source viewer configuration, a damage repairer, a presentation reconciler. What in the world are those things, right? And this goes back to the problem of when you're developing a big complex piece of code, a big part of it is developing the right abstractions, developing the right language to talk about the things you want to build, right? Somebody new comes in, they want to build some functionality. They don't even know how that functionality is called, what is the terminology to describe that functionality. So what we showed was a system where what you could actually do is take a piece of code that already has some functionality that you care about, and just exercise the functionality, right? Press a button that says, I'm about to show you something, right? And then go exercise the functionality, and then tell it, there, that thing that just happened, right? That's what I want my code to do, right? That's the functionality that I am looking for, right? And we're actually able to build a system that did this by combining a lot of data analysis, but it was actually quite effective even without the use of AI. And so just to end, I think there's no question that programming will change dramatically over the next 5 years, right? And simply going in and replacing human developers with AI agents in existing workflows is not going to work. We really need to think in terms of new tools and new development models and new ideas if we want to avoid a software crisis where we have enormous amounts of code that nobody understands and that have hidden vulnerabilities just waiting to blow up. Thank you.
Thank you so much for that very insightful talk, Armando. So we have time for a couple of questions. Anyone have a question? Here, either side.
Over there.
Sorry, can you put your hand up?
In the back.
There's a question.
Yeah, just speak up.
My blind spot.
Thank you so much for the great talk. You were talking about new software models, but one of the things I've seen over and over, of course, last 15 years in software development is how we keep on kicking to older models, right? Like going from object-oriented development, like you gave an example of, back to things like, function-driven development. What have you seen in terms of older models that have started to work better, right, in the world of working with AI and its verifiability for being able to make sure we're getting real bugs?
Well, so one of the things that you're starting to see a lot, for example, is after many, many years of people being very down on like the waterfall model, right? Who wants to go and write detailed specifications before they go and start building things, right? Well, it turns out now it actually makes a lot of sense to go and write detailed specifications before you start building anything, because the building part is really fast and pretty much automated once you have the detailed specification, for example, right? And I think you're going to start, I think that's probably the most salient example that comes to mind there, right now. But I do think that we're really going to have to rethink the software development process, given a lot of these new capabilities.
Yeah. What's your view on the programming languages and evolution of programming languages? Because, in the last 50 years, we have seen the ease of programming was the driver. So now that ease of programming is through the agent. So, and what if there is somebody in this room actually comes up with a more better programming language? Then what happens? Do you have any thoughts?
So this is a really good question, right? And I could probably talk for an hour about this. At a very high level, traditionally there has been this tension in the development of languages between the ease of writing and the ease of reading, right? And sometimes things that make it very easy to write end with code that looks like Perl, right? Where, write-only code and, good luck figuring out what it does later, right? I think the trade-off today is very much in the opposite direction, right? It doesn't really matter how long it takes to write to the thing, but you better be able to actually quickly look at it and analyze it. I think there is both a big opportunity and a risk right now. I think the big opportunity is that before, another big consideration is will people be able to learn how to use this, right? Will people want to use this language that they've never programmed before, right? And there was a lot of inertia. Suddenly, if all it takes to have the model use your language is to give it the manual, right? And it can program in whatever new language you have, a lot of that inertia goes away. But there's also a risk there that, at the end of the day, the tools are trained in the languages we already have. They're really, really good at writing code in Python and JavaScript and Java because there's a lot of that kind of code out there, right? If you want them to write code in your new language, suddenly they have to think a lot harder. They have to waste a lot more tokens just reasoning through the steps of how your language works. And that could actually even exacerbate the problem of inertia.